Let's pick up right where we left off at the end of the last video. So in the previous video, I had given you this A matrix, and I'd given you the P and the D that make up the PDP inverse diagonalization of A. So the big question, of course, is where does P and D, where do those come from? How can you find them yourself for a particular A? So let's go to the A matrix, and let's just find, for no particular reason, the eigenvalues and the eigenvectors. Just for fun. Let's give it a shot. Okay, so you know how to do that, right? You do the A minus lambda I. So finding those, let's see, it'd be 7 minus lambda. I'm just going to jump straight to the characteristic equation. 7 minus lambda, negative 4 minus lambda, minus negative 30, so plus 30, equals 0. There's the characteristic equation that would find our eigenvalues. Let's multiply this out. Let's see, we get lambda squared plus 4 lambda minus 7, so plus 4 minus 3 lambda, negative 28 plus 30, so plus 2 equals 0. That one happens to factor nicely enough. Lambda minus 2 and lambda minus 1. So our two eigenvalues happen to be 2 and 1. And look at that. Those happen to be the entries on the diagonal of the D matrix. Not a coincidence. And furthermore, any guesses on what the eigenvector is that goes with 2? Well, let's just find out. So for 2, it would be, subtract 2 from the main diagonal, so it would be 5, negative 15, 0, 2, negative 6, 0, and when you row reduce that, it becomes 1, negative 3, 0, 0, 0, 0. So x1 equals 3x2, and x2 equals x2, and factor the x2 out. Oh, look at that. 3, 1 is the eigenvector that goes with an eigenvalue of 2. So, and there's 3, 1. And I'm sure you can guess at this point what the eigenvector that goes with 1 is. The eigenvector that goes with 1 happens to be 5, 2. So really, once we can find the eigenvalues and the eigenvectors, we can build P and D, and therefore have P inverse as well. And that is actually the big theorem for this section, the diagonalization theorem. It says the matrix n by n is diagonalizable only, first of all, it has to have independent eigenvectors. That's the only way you can build your P. 2 by 2, you need 2 eigenvectors. 3 by 3, you need 3 eigenvectors. 10 by 10, you would need 10 eigenvectors. So as long as you have that, then A factors into PDP inverse with the diagonal entries of D are the eigenvalues, so the 2 and the 1. And the eigenvectors correspond to the eigenvectors in P. Okay, so that's just kind of what we discovered already. I'm not really going to prove Theorem 5. The book does a nice proof of it. But I think I'll just point out that the form we have here, let's see, let me get back to a different color. The form that we have, A equals P, D, P inverse. If I just rearrange that a little bit and multiply both sides on the right by P inverse, or sorry, by P, multiply both sides on the right by P, I guess I'll go ahead and just write that in there. P, P. Now that simplifies to A times P equals P times D. Keep in mind that P is the eigenvectors and D is the eigenvalues. And that's exactly what should happen, is multiplying the eigenvector by A should be the same as multiplying the eigenvalue times the eigenvector. And that's what we've got here, is the eigenvalues times eigenvectors, matrix times eigenvectors. So it sort of makes sense that that works, and if you look at the proof in the book, they basically just write that all out. They say here's the eigenvalues times the eigenvectors, here's the matrix times the eigenvectors, and note that they're supposed to be the same. But I won't beat that dead horse. I'll let you look at it if you're really curious. So there's my hand waving proof. I'm just waving my hand at that, saying hopefully you buy that. Okay, so I think we have the basic idea, and we really should just look at an example. Or maybe we'll even look at 3 examples. So these are 3 from the homework, the evens, of course. And the instructions here are just to diagonalize the matrix if possible. Keep in mind, not all matrices are diagonalizable. For 14, for some of them, they actually give you the eigenvalues, which is nice. Some of them, like 10 and 20, they don't. But let's just start with number 10. So here they haven't given you the eigenvalues, eigenvectors, anything. We know that's what we need to find. So if this is A, we need to start by finding eigenvalues and eigenvectors. So let's start with the characteristic equation of 1 minus lambda 2 minus lambda minus 12 equals 0, and that would be lambda squared minus 3 lambda plus 2 minus 12, so minus 10 equals 0. That factors into lambda minus 5 and lambda plus 2. If you're not a factoring whiz, I mean, of course, as a math teacher, I should be telling you, like, review your factoring. So review your factoring, but that's not the point here. Feel free to use quadratic formula or a quadratic formula program that you have in your calculator, or graphing it and looking at the zeros, whatever. Some way, solve the characteristic equation and find out that the eigenvalues are 5 and negative 2. So that already gives us the, so we'll have P, we'll have D, P and D, and P inverse. That already gives us the D. So I know the D is going to look like 5, 0, 0, negative 2. And by the way, it doesn't matter which order you put the eigenvalues on the diagonal, as long as you put the eigenvectors in the same place. So if you put 5 in the first column, then the eigenvector for 5 needs to go in the first column of P. And you could do it the other way around. If you want negative 2 first, just put the eigenvector for negative 2 first. Anyway, so let's finish this off by finding the yes, let's finish this off by finding the eigenvectors. I guess we'll just start with 5. Yeah, I know. We could start with negative 2 instead. No, 5? All right, we'll go with 5. So starting with 5, you're just not happy no matter what I do. Starting with 5, it would be, so subtract 5 from the main diagonal. So that would be negative 4, 3, 4, minus 3. And we are augmenting that with 0, 0, and row reducing. And yeah, obviously the row reduction isn't hard here. Just add 1 of the first row to the second row. And again, feel free to do that on a calculator or by hand, whichever one seems easier. So the equation here would be negative 4x1 equals negative 3 x2. So x1 equals 3/4 x2, and x2 equals x2. So the eigenvector is any multiple of 3/4 1. And you certainly can use 3/4 1. There's nothing wrong with that. It's typical to choose your x2 so that you don't have to mess around with fractions, because who wants to mess around with fractions if you don't have to? So if you choose x2 to be 4, you can look at the eigenvector here as being 3, 4. So I will pick 3, 4 to be the eigenvector that goes with 5. So I'll put 3, 4 there. We still need to do the same thing. We need to find the eigenvector that goes with negative 2. And I'm going to skip the work for that one, but that one comes out to be negative 1, 1. So negative 1, 1 there. And we have found the P and the D. By the way, the book doesn't even bother finding the P inverse for the diagonalization. That's definitely not their focus here. So you don't bother. I mean, you could. Obviously, you can find the P inverse. But once we're beyond 2x2s, you're probably just going to grab a calculator to find that P inverse anyway. So the P and the D are considered the diagonalization of the matrix A. Okay, so that's fine for number 10. And again, if you look in the back of the book, they might have the 5 first and then the negative 2, or they might have the other way around. They might have the negative 2 and then the 5, in which case the columns here will be reversed. Either one works. Okay, so let's take a look at 14. The nice thing about 14 is they've already given you the eigenvalues, and there's only 2 of them, which is interesting. So let's go ahead and take a look at what happens with one of those. It's not clear to me how I'm going to build my D with only 2. But let's go ahead and start working on finding the P. So let me use lambda equals 2 and just see what happens here. I'm going to subtract 2 off the main diagonal. So that would be 0, 0, negative 2, 1, 1, 2, and 0, 0, 1. And if I'm augmenting that with zeros, this would say negative 2 x3 equals 0. So x3 equals 0. The next one would say x1 equals negative x2 minus 2x3. And the last one, again, says that x3 is 0. Which we already knew. Let's see. So we have x1 equals negative x2 minus 2x3. We've got x2 is free. x2 is x2. And we've got x3 has to be 0. So let's work on factoring. So pulling x2 out of the first column, that'd be negative 1, 1, 0 times x2 plus, and then pulling x3 out of the next column, negative 2, 0, 0. Turns out there are actually 2 eigenvectors that go with the eigenvalue of 2. And if we had actually solved the characteristic equation ourselves, we would have found that the solutions were actually 2, 2, and 3. In other words, 2 has a multiplicity of 2. They cleverly did not tell you that here when they were giving them to you. But that does mean that there are So when we're building our PDP inverse, let's see, let me put it down here. Our P, so this is still for number 14. Our P, D, P inverse, which we're not going to bother to calculate. That means that 2 is a multiplicity of 2, so 2 and 3 are the eigenvalues, and 0, 0, 0, 0, 0, 0. So there's our D. And there are 2 linearly independent distinct eigenvectors that go with 2 and 2. So negative 1, 1, 0, negative 2, 0, 0. And now we just need to repeat this process and find the eigenvector that goes with an eigenvalue of 3. And maybe I will go ahead and finish that off. I know you know how to do it by now, but let's see. If we're subtracting 3 from the main diagonal, it's negative 1, 0, 2, 1, 0, 2, 0, 0, 0. And if we continue, so yeah, and augment. Continue to row reduce here. Add the first row to the second row. This becomes negative 1, 0, 2, 0, 0, 0, 4, 0, 0, 0, 0, 0. Okay. So the the second row here says that 4x3 equals 0. So once again, we know that x3 has to be 0. And the top line says that negative x1 equals 2x3. So since x3 is 0, that means that x1 is 0 also. So we've got something like x1 equals 0, x2 is x2, x2 is free, and x3 is 0. So after factoring the x2 out of that, you get 0, 1, 0 for my other eigenvector. All right, so let's put that one in there as 0, 1, 0. There's the diagonalization for 14. Our 2 eigenvalues that actually turned out to be 3 eigenvalues. And that works as long as there are linearly independent eigenvectors for 2 and 2. Otherwise, if the columns of P are not linearly independent, then P is not invertible, and we can't find P inverse, even if we were going to. But 2 and 2 created 2 linearly independent eigenvectors, and then there was a third linearly independent eigenvector. So we're good to go. We have diagonalized number 14. All right, let me do a little bit of erasing, and then we'll tackle number 20. Okay, for 20, notice first of all, this is a triangular matrix, so we know the eigenvalues. The eigenvalues are 3 and 2, and they're both multiplicity 2. So the eigenvalues are 3, 3, 2, and 2. If this is diagonalizable, the diagonal entries on the D will be 3, 3, 2, 2. We just need to make sure that there are linearly independent eigenvectors for each of these, for all 4 of them. So let's start with the 3. 3 minus 3, so 0, 0, 0, 0, 0, negative 1, 0, 0, 0, 0, negative 1, 0, and 1, 0, 0, 0. Okay, this is a pretty sparse matrix, but let's see what we can work with here. We've got, I'm going to write them in a different order. So the bottom row, which I would flip up to be the top row, says that x1 equals 0, and this row right here, the second row, says negative x2. Sorry, we need to augment this. There are four variables. And x2, negative x2 equals 0. So x2 equals 0. The third row says that x3 equals 0. X4 is a free variable. So we are actually going to get, when we factor x4 out of this, we're not just getting the 0 vector, which doesn't even work as an eigenvector. So we are getting an eigenvector, 0, 0, 0, 1. But notice we're only getting one eigenvector. And we needed 2. So that's already out. It turns out if you start with the 2's, you do actually get 2 free variables, and you'll get 2 distinct eigenvectors out of that one. And the one distinct eigenvector we get here gives us only 3. And we need 4. So number 20 is not diagonalizable. Okay. So I think the first couple problems in the homework assignment are slightly different than the 3 that we've looked at already, but I think you'll be able to tackle them. And then these 3 will give you a good start on the rest of the homework assignment. So this video ended up being way longer than I planned. Sorry, I try to keep them like 10 minutes, and this one's clocking in at 21 minutes. But I do think you're ready to go now. So tackle the homework, and I will see you in the next section.